this follows up nicely with net radiation, because we just talked about the fluxes at night, and Mark said, okay, what happens at night? The incoming is 0, and if the sky is colder than the ground, there's a continuous flux of radiation to the cold night sky. And the surface can get very cold. So, and it's underappreciated how cold surfaces can actually get at night when the sky is clear. One of the examples of the power of this is if you build an insulated box, especially a tall box. I'm gonna draw this here. If we build, let's say it's a circular cylinder like this, and it's well insulated. So we fill this is open on the top, but it's full of insulation. And now we put at the bottom a dish of water. And we paint this black to have a high emissivity. And it's just open. We take this cylinder and we put it outside in the summer on a clear night. This is a PhD comprehensive exam question I like to ask. What happens to the water? This is room temperature. Now we start. I should have a little blue for the water, right? And shallow dish of water. The air temperature out here, let's say it's, doesn't matter. Let's say it's 30 degrees C. It's a pretty warm night, but it's clear. What happens to the water? Does it change temperature? Yes. Does it get hotter or colder? Colder. It's radiating to the clear night sky. When you went outside with those things and the sky temperature is minus 30 or some cold temperature, the incoming radiation is real tiny because it's cold. It can't warm up by conduction and convection because we've insulated this thing, and if the wind is blowing, it'll keep it warm. But if it's a calm night and it sits there, I've read this in some physics book a long time ago, and so I built this in my backyard and got it all instrumented and put thermocouples in here and sat out there at night and measured this thing. It gets colder and colder. It's continuously radiating to the sky, and even when the air temperature is 30 degrees, the water freezes inside this column because it's coming to equilibrium with the sky, a super cold temperature. And this isn't just a physics experiment. People can use this in the tropics to keep food cold. You can radiate to the sky at night, and then in the daytime you just cover it, and you cool it down at night, and no electricity, just the physics of radiation to the sky. So this gives you a sense of the power of long wave radiation at night. Now what happens to a surface, a leaf of a plant, or a surface at night when it's clear? If it's cloudy, not much happens because the clouds are low and they're similar to ground temperature. But if it's clear, they cool off. And you run models, because if you buy a net radiometer and you measure it and you model it, and we see conditions where it's easily 5 degrees C below air temperature. And there's cases when it's been 10 degrees C below air temperature at night. So that led us to make this sensor a radiation frost sensor, which is a way cheaper version than having to buy a net radiometer and run all these models anyway, to predict surface temperatures at night. And it's black, so it has a high emissivity. It's similar, like 0.96, it's similar to leaf surfaces, black disk, and you put it outside, and we measure then the temperature of the surface of that disk with a tiny thermistor. I'll show you some data in a minute, but you can see how this simulates a leaf temperature, or there's another sensor here in a tiny little thermistor, a bud of a plant. And so this is called, when a surface freezes and the air temperature never got below freezing, that's called a radiation frost. And it's a huge deal worldwide for commercial fruit producers where their sensitive flowers are coming out. You can see those in the background. Little buds in the spring coming out of that plant. And if those get below freezing, they can lose millions of dollars in commercial yield because their flowers freeze. So because it's such a big deal, they start wind machines, they start sprinkler irrigation to freeze water. They do all kinds of things to protect their crop, but they need to know exactly when to start this. So I called this radiation frost sensor, or also a nighttime surface temperature sensor, and it measures these physical principles of radiation transmission and temperature. I think my next slide, we don't have one of these here. Did he?
I'll pass.
Great.
Go ahead.
We could have picked some even worse data than this, but this is a typical data for a night in our spring in the northern hemisphere, where this is that sensor and the temperatures are all coming down together, but it's a clear night, hours from midnight. We're getting close to midnight. Now look at the big leaf sensor cooling off, and a little bit, and when it's calm wind, this is wind speed, it really starts to diverge a lot because the wind will warm it back up when it gets cold. But if there's not a lot of wind, it just keeps getting colder. And right in here somewhere, if you were only measuring air temperature, you wouldn't be worried about a frost. And the air temperature is +3 degrees C, but the leaves are already starting to freeze. And it gets bigger and bigger. And finally, 4 hours after midnight, the air finally gets below freezing. But the plant has been below freezing for quite a while. So frost is the big economic thing for freezing of sensitive buds. But it also gives you an indication of nighttime surface temperatures. And we talk about measuring those in the day and predicting water loss. And at night, it's more of models and predicting rate of development of plants. If we understand the night temperature, we can predict rate of development. So it's a pretty simple sensor. It's not an expensive sensor, and it's been particularly useful to commercial tree crop producers to tell when to turn on their fans to protect their crop at night. So this is a pretty simple story once you understand the concept of net radiation. So I'm going to switch into the next topic, which is chlorophyll. But any questions on that radiation sensor?